Okay, so the last section on graph theory and the last section for exam 2 here is isomorphisms of graph, okay? Iso again meaning same and morphism meaning shape. So basically they're the same graph. So I didn't really want to show you that. If I just, I generally do this when I meet with students live and in the flesh. I just, tell them take out a piece of paper and just label 5 vertices wherever they want, A, B, C, D, and E. And then connect the following, right? Do A to B, B to C, C to D. So you do it on your picture. And sometimes, most of them look like the one on the left, but sometimes, they look like the one on the right. Or which one of these is actually correct? I mean, if you follow the directions, they're both correct. You can equally, you can arrive at both pictures. Right? In other words, they're really the same. They don't look the same, but they are the same. They have the same properties. So two graphs, G1 and G2, are isomorphic if there exists a bijection, there's that word again, right? A bijection from V of G1 to V of G2, and a bijection G from the edges of one to the other, so that if E is incident to V and W in G1, then G of E is incident to F of V and F of W in G2, right? In other words, you get that one-to-one onto function, right? When we did the counting stuff and we did cardinality, how did we show infinite sets maybe are the same size? You exhibit a bijection. You have a one-to-one onto relationship. It's the same thing here. No different. So two graphs are isomorphic if and only if, for some ordering of the vertices, the adjacency matrices are equal. Right? That's an if and only if statement. Okay? It goes both ways. Are these isomorphic? Why or why not? Well, again, isomorphic meaning basically the same properties, right? So let's take a look over here. That's a vertex of degree 4, right? Here's a vertex of degree 4. Here's another of degree 4. Here's another of degree 4. Here's another. How many degree 4 vertices do we have on the top one? It looks like only that one. So there's no way, right? No, they're not isomorphic. They're not remotely the same. Everything has to line up. Same number of vertices, the degrees. If you have 3 vertices of degree 3 in one, you better have 3 of degree 3 in the other. So no, these are not isomorphic. So when you want to show things aren't, you just need to really find a property that one has, the other one doesn't. Are these isomorphic? Again, take a look. Look at the different properties. Is it possible? Here we have 2 of degree 3. Here we have 1, 2, 3, 4, right? No, they're not. They're not the same graph. So a graph is planar if it can be drawn in the plane without its edges crossing. So this kind of was related to the first part that we did here with graph theory. Remember I told you I gave you K4 and I said you could draw it like this. That's K4. That's totally fine. Or you can draw it like this, right? Why would I want to draw it like this? Well, that's planar. This one isn't. So again, a graph is planar if it can be drawn without the edges crossing. If it is connected planar and it's drawn, it's divided into these regions called faces, which are characterized by the cycle that form the boundary. So here's an example of a planar graph. Right? No edges are crossing. And we have these faces or these boundaries. So A is bounded by 5, 2, 3, 4, 5. If you go around that cycle there. Similarly for C, for B, and then they have the whole outside, which we're going to call D. Okay. Now it turns out in this particular example that the faces is equal to the edges minus the vertices plus 2. Right? That's not a coincidence. Actually, Euler proved that this holds true for every connected planar graph. That relationship is true. So here with example 27, we're going to build up to another theorem here, but we need a few more definitions. The top graph, we say V1V and VV2 are in series. So this is kind of in series here. So the bottom graph is obtained by cutting out V in the top graph and just connecting V1 to V2. That's actually called a series reduction. Okay, so here these are in series, and then this is what is called a series reduction. So why am I mentioning that? Well, because we need another definition before we get to the theorem. The other definition is two graphs, G1 and G2, are what are called homeomorphic. If G1 and G2 can be reduced to isomorphic graphs by performing a sequence of series reductions. So if you can do some series reductions and make them look the same, reduce them to isomorphic graphs, then they are what are called homeomorphic. And we need that information for the following theorem. So here, example 28, we have a G1 and a G2. Notice that for G1, I've done a series reduction here and here, and also here, in order to create G. Right? That's how I got from there to there. Over here from G2, I did a series reduction here and here, and I was able to create G that way. So it looks like G can be created by some series reductions on G1 and G2. So we say G1 and G2 are homeomorphic. They can both be reduced essentially to G. So why do I care about this? Well, I care about this because that's how we use Kuratowski's theorem. So Kuratowski's theorem says a graph is planar if and only if G does not contain a subgraph homeomorphic to K5 or K33. Those are essentially your minimums. Anything over that's not going to work. So K5 and K33 are most definitely not planar. So if you have a graph, it's planar if and only if there's no subgraph that is homeomorphic to K5 or K33. In other words, there's no subgraph that can be series reduced down to look like K5 or K33, because those are not planar. And so you're going to do this on the worksheet. Okay. So here for the first one, we're just determining isomorphism. Okay, again, look at the characteristics, same number of vertices, same number of edges, degrees of edges. That usually gives that away. For number 2, I want you to show that G is not planar. In other words, try to find K33 or K5. I'm giving you a hint here. You're going to want to find K33. K33 is the complete bipartite graph, right, on 3 and 3, right? So this goes to all 3, this goes to all 3, and this goes to all 3, okay? And there's no, these are the separate pieces, the disjoint classes of vertices. So see if you can find that in there by some series reduction. It shouldn't be that bad. Okay.